Okay, continuing on with homework 2. I think I might have called the last one. I'm not sure if I called the other one homework 3 on accident. I accidentally wrote homework 3 at the top of the page. I erased it and put homework 2. This is homework 2, problem 1. We're on homework 2, problem 2. Right. So let me read the problem statement. No, this one right here. Okay. And so this is the arrangement we have of some blocks and pulleys. Block A starts from rest and moves upward with a constant acceleration, right? And then we know that after 8 seconds, the relative velocity of the weight B with respect to A is 0.6 meters per second. We don't know which one that's going to be, but we can establish how they move with respect to each other as we're going through this. And we want to find the acceleration of A and acceleration of B. And by the way, if A is constant, then B must be constant because they're attached to each other. So here's the information that we have. And let's see if we can work through this. I haven't actually solved this problem, so I'm not 100% sure that what's going to happen here. The first thing we want to do is get our datum going on here. And the first thing we want to do is write out all our, all the things that are necessary as part of our work. But I'm going to use this right here as the datum, and this right here I'm going to call, for the time being, I'm going to make downwards positive because that's kind of what we've been doing, right? But that's that position right there, and I'm going to have this right there as B for B. We will have some constant thing in here in between this length right in there that we can ignore if we'd like. So here's going to be YB. And I'm just doing that to set up the interrelationship between the two. If it makes you feel any better right here, we can have like this little constant right here. We'll just, I don't know, I'll just call it C, whatever. That distance in between there, right? That'll help. All right, so we want to write the length of the rope. And so we start right here. We go, like this is going to be 2 times YA, right? So 2YA, and then there's going to be plus a YB. Let's see if I'm going to do this correctly right here. Yeah, and then we're going to have this little piece right here. So it's going to be YB minus a YA. So it's going to be plus YB minus C, and then minus YA. All right. That C is going to go away because we're about to take the derivative of this. But notably, one of our YAs of here actually goes away because of this, and we actually have 2YB, right? So I could do that as an in-between step if you'd like, or we can just go ahead and take the derivative of this and group things together, right? So we can see that it's going to be VA plus 2VB, right? Maybe not expected because there's 2 cables right here, but the interplay between those things gets canceled out. And let me take a look. I have a similar problem over there. Yeah, I got it right. Cool. So we can also say that the acceleration of A plus 2 times the acceleration of B, right? So over here we could say the acceleration of A is equal to negative 2 times the velocity of B, and the acceleration of A is equal to negative 2 times the acceleration of B. So we have that relationship. All right, so we also know that let's see if I'm going to say this correctly. We also know that VB with respect to, and we always know that they're going opposite from each other, right? So VB minus VA, I'm going to get the direction of this thing correctly, right? So A is going upwards, so B must be going downwards, right? So that's one thing that we know. So the velocity of B with respect to A is going to be the velocity of B minus the velocity of A, right? And we know that this is positive and then this is negative right there. So we could actually put those in there if we like. We know that that's going to be equal to 0.6 meters per second, right? And we could also say, oh, by the way, we know that velocity is related that way. We also can find the acceleration from this, right? So we could also say the velocity of B with respect to A, right, is, now I should say, does it start from rest? I think we should have said that it starts from rest. I want to double check on that there. It starts from rest. Okay, so that helps out. So the velocity of B with respect to A is equal to the velocity of B with respect to A at the beginning plus the acceleration of B with respect to A, right there, right, times time, right? So this is another thing that we can use. I'm not sure I'm going to need this. I'm pretty sure I'm going to need this, right? So to find out the absolute values of these things. So this is going to be 0.6 right there, right? And this is going to be 0. And so we have the acceleration of B with respect to A at 8 seconds. And I should probably put this as, I decided to call that 2 right there. Yeah. So it's at 8 seconds. So we said the acceleration of B with respect to A is now going to be 0.6 divided by 8. And this be small number, 0.075. And these are going to be meters per second squared. Okay. All right, so what else do we have going on here? I shouldn't record these live, should I? I should actually do the problem up. But anyway, it makes the video longer. I don't want you to waste time, but I want you to hear like the thought processes, so maybe that by doing it live right here. So we have where to go from here. We need the acceleration of A and the acceleration of B. And we know this value right there. So what we could say here is the acceleration of B with respect to A is equal to the acceleration of B minus the acceleration of A. But we know that the acceleration, for instance, we know the acceleration of A is negative 2B. So we could say that acceleration of B minus 2AB, right, is going to be equal to this value right here. So we have equal to, so it's going to be minus, so that's going to be 3 times the acceleration of B and equal to 0.07500 meters per second squared, right? So we have the acceleration of B. We found the acceleration of B from that, right? So this is going to be that divided by 3, so it's 0.02500 meters per second squared, and that means obviously we can now also find the acceleration of A. This is going to be, all right, and we know that A is going up, so this must be going down, right? I didn't bother with the positive and negatives right in here, but I know from the beginning that this is going up, and I know from here these must be opposite from each other. So, and I know that the acceleration of A is 2 times the acceleration of B, negative 2 times the acceleration of B, or negative 2 times 0, and this is, make that a negative one, right? If I'm going negative and positive on the thing. So it's a negative 0.02500. So all we have is a positive 0.05000 meters per second squared, and it's going upwards. All right, so we actually solved this one and this one, and now we want to have the velocity of this and the change in position at 6 seconds. So I call this one time 2 because it happens after this. So I just want to go time 0, times 1, the time at 0, the time at 0.1, the time at 0.2. So I'm trying to keep track of it by subscript numbers. I don't know if I'll always do that and be it'd be good practice to try to be organized like that. But now we know that that A starts from rest. I think in the problem it says that, right? It says block A starts from rest, and therefore we know that block B starts from rest because the velocity relationship right there, right? So the velocity of B, and we can call that B1, right? Because it's up here, and that's the time B1. Maybe I'll even write that B1. Delta Y is, I guess, delta Y1, right? Okay. So that's going to be the velocity of B, in original, and I didn't do the parentheses as part of that. Sometimes I'll be consistent there. Plus the acceleration of B times time 1. Right, and we know that this is going downwards, so that must be going downwards onto the thing, and we know this is 0. It starts out, and so we go plus, and we go negative 0.025, and then the time is 6 seconds. So I just multiply that by 6, and we have that's gone 0.1500 meters per second downwards, right? Because it was negative. I could put in the negative down here. Do it in 2 steps. Don't put an arrow if you have a negative, right? It doesn't work right? So we can rewrite that at the end. We don't have to put it right here. And then the change in position, well, you could think of this as YB1 is equal to YB0, and just have that because we want to change, we're going to make that 0, right? We don't know the actual distance of the thing. All we want is the delta as part of our answer. And then plus VB, call it 0, times time 1 plus 1/2 acceleration of B times time 1 squared. I think I have everything I want in there, so we're gonna use that as the we can actually just bring this over and call it delta Y. B1 minus YB1 minus YB0 is delta YB1. Right? And then it starts from rest, so it doesn't really matter. And this is 6 seconds. And then we have plus, but we have minus 0.025, and then times our 6 seconds, but squared, right? And so we would find that YB1 is just going to be that 0.025 divided by 2, but times 36. And so we get 0.4500 meters. It's actually negative because of that right there. So we can give our answers for all of this. We have answers. And for part A, we would say that the acceleration of, and make it a vector, acceleration of A is equal to 0.0500, and that's 3 sig figs right there, right? Meters per second squared upwards. Acceleration of B is 0.0250 meters per second squared downwards. And then part B here is the velocity of B, we'll call that 1, is equal to, where is it? 0.150 meters per second down, and then the delta Y B1 is equal to 0.450 meters, and it is also a downward thing. And well, I didn't really make that a vector. onto the thing, but I guess it is kind of a vector now. But that's how I would approach this problem. Summarizing, I'm doing these videos because I want to try to help you answer that question. How was I supposed to know that? That's what you're supposed to be asking yourself. Well, you can kind of see there's a routine going on. We use that conservation of rope kind of idea, and try to have this interrelationship between A and B. And then also know we have the relative velocity thing. And we can know that the relative velocity, when these things are connected to each other, the relative velocity has to behave in the same way for a constant acceleration problem here, so that we can find what that relative velocity, and we can find the relative acceleration. So by that definition, and combined with this interrelationship, we can find out what the actual values are going to be. And it always looks easy in hindsight. It always looks easy in hindsight, but the problems really baffle on the front end. So that's the real thing that we're learning, is how to get from being baffled to weaving our way to finding a solution strategy. And the only way to do that is to do it on your own, not to just follow what I'm doing. So only watch the videos when you're just completely desperate and don't know. But then do the next problem on your own. You might even want, I don't know, try problem 3 first in some homeworks, and so that you can actually try problem 2 on your own, because it's not always, but a lot of times problem 3 is going to be harder than problem 2, which is going to be harder than problem 1. So you might want to try to maybe have that kind of strategy, because remember, we're exercising our brain, and the only way you're going to be prepared for an exam is if you're able to cross that, like, figuring out kind of threshold. So I will do another video for problem 3.